Alrighty, in this video we are going to be talking about improper integrals. In this case, we're going to be talking about type 2, which is your discontinuity. So let's say that you have a vertical asymptote. So make sure that you watch the day 1 video so that you understand what's happening here. We have an arbitrary t value right here, a line t, and we are going to get closer and closer and closer and closer and closer to my vertical asymptote. Now, my vertical asymptote, I am approaching it from the left side. So for your limit, you want to make sure that your limit is from the left. So you have the limit as t approaches b from the left, from a to t of f of x dx. Likewise, if we have something like this, and your vertical asymptote is on the left side, and we have some arbitrary line t right here, and we're going to move that to the left, you'll notice that my vertical asymptote, or my line is going to be approaching the vertical asymptote from the right side. So that's how we get this lovely thing right here. Once again, just like the previous video, ooh, that should not be that. The improper integral from a to b f of x dx is called convergent if you have a limit. If it doesn't have a limit, it's divergent. And if you have a discontinuity at c, where c is between your two intervals, then we can split up the improper integral. So you go from a to c and then c to b. If they're both convergent, you can add them together. If they're not, aka one of them's divergent, then the whole thing's divergent. Once again, just like the improper integrals on day 1, this is a two-step process. We are going to evaluate the definite integral, simplify, then we are going to evaluate the limit. Okay, so looking at number 1, I have the integral from 2 to 5 of 1 over the square root of x minus 2 dx. Notice how here I have a vertical asymptote at 2. Which is my lower bound. I don't know what this looks like, but I do know that if this is my graph and this is my line right here, and this is 2 and this is 5, and I want to go to 2, I'm going to be approaching the asymptote from the right side. So whenever I am making my limit here, you want to make sure that it is 2 to the right. So I have my limit as c approaches 2 to the right of t to 5 of that lovely thing, which I'm going to rewrite as this right here. I am going to be using u substitution. Use x minus 2, dq is 1. So now you have the limit as c approaches 2 from the right of, let's see, u to the negative 1/2 dq. Now, notice how I don't have my bounds of integration yet, and I don't know if I talked about this in the other video or not, but remember that if you're using u substitution, you want to make sure that your bounds are in terms of u. So do not put t and do not put 5 here, or else you will not earn full credit. Instead, you want to make sure that your bounds are in terms of u, so I'm going to plug in 5 and t into the u minus 2 right here. That is going to give me 3, and this is going to give me t minus 2. Once you do that, then you'll earn full credit for your limits. Okay, so that, if I were to up my power and divide, that's going to give me 2 u to the 1/2 from t minus 2 and 3. Going to evaluate. So that's the cube root of 3 minus the cube root of t minus 2. If I'm approaching 2 from the left, I'm going to pick a small number like 2.01. And eventually this is going to be 0. So then you have 2 root 3 minus 0. Oops. 2 root 3 minus 0, or just 2 root 3. All right, let's say we have number 4, where we have the integral from 0 to 3 of 1 over x minus 1 dx. And you might think for this problem that we could use u substitution and call it a day. However, you'll notice that your vertical asymptote is at 1, which is between 0 and 3. Had this been something else where 1 wasn't between your two bounds, then you could have used u substitution. But you can't in this example because you have a vertical asymptote at 1, meaning that I have to, I'm going to have to split this up into two integrals. And once again, you want to make sure that this integral here and this integral here both converges. If one of them do not, then we mentally cry because we did a lot of work for nothing. Okay, so we have a vertical asymptote at 1. So we have the limit as t approaches 1. And then if I were to look at this mentally here, and let's say that this is 1. Well, yeah, that's 1 right there. Here's 1. And we have 0 to 3. Then we are approaching it from the left side. So the left side. So here's 0, and then here's 1, the left side. And then if this one right here is going to be the right side. But we're going to focus on this one first to see if it converges. All right, so you have the limit as t approaches 1 to the left of ln of x minus 1 from 0 and t. The limit as t approaches 1 from the left of ln of t minus 1 minus ln of negative 1, which is just 0. So now you have this right here. All right. So what I'm going to do is figure out what this approach is right here. If I were to make my ln, it looks something like this. And if I were to plug in something from the left, let's say I pick 0.999999999, then I'm going to have ln of negative 0.00000001. You get the idea. And this is essentially the positive value of that. And that, if I were to look at my graph, approaches negative infinity. And it diverges. Since we have negative infinity and it diverges, we know that I don't care about this one right here, just because this already diverges, meaning that this whole problem, sad face. All right. Let's do 5. 5 is an integration by parts problem. So we have to use parts here. But before we do that, let's go ahead and write my limit notation first. Remember that this is ln of x, so it looks like that. Your 0 is where we have my vertical asymptote. If I were to make an arbitrary line, I'm moving my 0 from the right side. So now I have the limit as t approaches 0 from the right of t to 1 of ln of x dx. Limit as t approaches 0 from the right. And then remember that we have to use integration by parts. By now, I feel like we've done a lot of problems in terms of ln of x, that you should know what the integral of ln of x is by now. I don't, so I am just going to use good old by parts and call it a day and see where that takes me. Okay, so uv minus v du, 1 over x times x is just 1. So now I have that. So now I have the limit as t approaches 0 from the right of x ln of x from t to 1 minus x from t to 1. Okay. Going to evaluate, so now I have the limit as t approaches 0 from the right. If I were to plug in 1 here, it really doesn't matter because ln of 1 is 0. So now I have 0 minus t ln of t minus 1 minus t. Going to make this a little bit prettier. So I have negative t ln of t minus 1 plus t. Now this one right here, since I'm going from the right of 0, and this is just a linear function, this is just 0. So the only thing that I have to worry about is this thing right here. All right, so if I were to do t, this is going to approach 0, and this right here, ln of t, remember that ln of t looks like this right here, and if I'm approaching it from the right, this is going to give me negative infinity. So I have 0 times negative infinity, which is an indeterminate form, which means that in order to use L'Hopital's, I need to change this so that it looks like 0 over 0, or it looks like infinity over infinity. Well, I don't know how to change ln of t so that it is in the denominator, but I do know how to change t. It looks like that. And remember that 1 over t looks something like this. So if I were to approach 0 from the right, I'm going to get positive infinity. And then with ln of t, that's the reflection over the x-axis. So that negative ln of t, that looks like this now. And if I were to approach 0 from the right, that's going to be infinity. So I have infinity over infinity, which means I could use L'Hopital's rule. I'm too lazy to write that, but you get the idea. So now you have the limit as t approaches 0 from the right of negative ln of, well, negative 1 over t over negative 1 over t squared. And that's going to be t. So now you have the limit as t approaches 0 from the right of t, and that's just 0. So this thing is just 0. So now you have 0 minus 1 plus 0, which is just negative 1. Crazy. All right, one more, and then we'll talk about the FRQ. Let's do 9. 9's a partial fraction problem. Notice how we're doing a lot of integration by parts, and we're doing a lot of partial fractions, okay? All the integration techniques that you need to know for BC. I'm going to factor. So that is minus 2 plus 1. I have the integral from 0 to 4 of 1 over x minus 2, x plus 1. Notice how the 2, we have a vertical asymptote here, so we are going to have to use improper integrals for this part right here whenever we take my partial fraction. My x plus 1, I really don't care, so we can evaluate this, but it's important to look at the improper integral first before we evaluate this right here if this converges. But first, we got to go ahead and make our little decomposition. What is it? 1, 2, go to 1. Okay, so x plus 1, x minus 2. You don't have any coefficient, so a plus b is 0. You have a constant, so a minus 2b is 1. Going to subtract. B minus negative 2b is 3b is equal to negative 1. B is equal to negative 1/3. And then a has to be 1/3. So now I have the integral from 0 to 4 of 1/3 x minus 2 plus negative 1/3 x plus 1. Now, like I said, this fraction right here is going to be improper. This one right here, I'm going to split it up so that it doesn't deal with this right here. This fraction on the right is not improper, so we can evaluate this. But like I said, we probably want to evaluate this first to see if it converges, because if it doesn't, and if you did this first, then you just wasted a lot of time, because then this is divergent if it is. All right, so I'm going to split it up, 0 to 2, 2 to 4, and then, of course, we still have this, which I'm going to rewrite just so that I don't forget about it. Okay, and then what I forgot was to put the limits. So you should probably go back and do that. Oops. Well, and honestly, you only need the limits. Well, just kidding. Just kidding. We are going to evaluate this, and then we're going to use the limits, because now we know that it's improper. All right, so this is my upper bound. So that means I'm going to approach it to the left, which means that I have the limit as c approaches t from the left of 0 to t of 1/3 x minus 2 dx. Limit as c approaches t to the left of 1/3 ln of x minus 2 from 0 to t. Limit as c approaches t from the left of 1/3 ln of t minus 2 minus ln of 0, or ln of negative 2, sorry. Which is ln of 2. So far, so good, because we have ln of 2, and then we have this 1/3 right here. We have to figure out what this is right here. And this is kind of similar to what we did right here. Notice how this is 1 to the left, and this was x minus 1. And this is 2 to the left, and t minus 2. So unfortunately, this one right here is going to suffer the same fate that we did earlier in terms of number 4, where it diverges. So this thing diverges. We cry, because then everything else is divergent. So number 9 diverges. See how you want to do your improper integrals first, because if you evaluated this right here, then sucks for you. Boo. All right. At this point, pause the video and do this FRQ for 15 minutes, and then play it once you are ready to do so. All right, so we have 1 over x squared minus x minus 6, and a portion of the graph of x is shown in the figure. We want to find the value of a in which the limit as x approaches a to the right of f of x is infinity. Well, in order to do that, we probably need to figure out my denominator and factor that out. So that's going to be x minus 3 and x minus 2. Nope, plus 2, sorry. X minus 3 and x plus 2, which means that I have an asymptote at 3 and at negative 2. Now notice how here, this is already the y-axis. So we're only looking at quadrants 1 and 4 right now, and I guess 3 technically. Because of that, this tells me that my a value is going to be 3. Because that is my vertical asymptote. That is the positive side of the graph. Right here, or the right side of the graph. Okay, part B says, let A be the region that is unbounded on the right, but bounded everywhere else by the graph of x, f, the x-axis, and on the left by the line x is equal to 4. And then we want to show that the area of A is ln of the fifth root of 6. This is 3 right here, so that I really don't care. So it's essentially asking you, find this area right here. So we have the integral of 4 to infinity of 1 over x minus 3 x plus 2 dx. Lucky for you, we aren't going to have to do something like number 9 here, so that's good. But we still need to do partial fraction decomposition. So go ahead. Okay, so you don't have a b and a coefficient, so that's 0. 2a minus 3b, your constant's going to be 1. You're going to have to multiply the top. B is negative 1/5. All right, since b is negative 1/5, that means a is 1/5. So that is going to give me my integral from 4 to infinity of, let's see, a is 1/5. So 1/5 x minus 3 plus negative 1/5 x plus 2 dx. Because we do not have any asymptotes here between my two intervals, this is just a type 1 problem that we did in the previous video, where we have the limit as t approaches infinity of 4t 1/5 minus 3 1/5 x minus 2 dx. The limit as t approaches infinity let's do this. We have 1/5 ln of x minus 3 minus 1/5 ln of x plus 2. This is from 4 to t. I am going to combine and we have 4 to t. That way it's easier for me to look at this and it's prettier. Now I have the limit as t approaches infinity of 1/5 ln of t minus 3 over t plus 2 minus ln of 4 minus 3 is 1, and then 4 plus 2 is 6. Right, as I approach infinity here, notice how my degrees are both the same. So I'm going to look at my coefficients, and since my coefficients are both 1, 1 over 1 is just 1. So this means that this will approach 1. And ln of 1 is just 0. So now I have 1/5, 0 minus ln of 1/6. So now I have negative 1/5 ln of 1/6. Remember that one of the log properties is raising your coefficient as a power. So now you have ln of 1/6 to the negative 1/5. I'm going to use this 1/6 and this power of negative 1 to give me 6. So now I have ln of 6 to the 1/5. And then I'm going to change the 1/5 and rewrite this in radical form so that I have ln of the fifth root of 6. Yay. All right, part C, so let's find the area of the region B bounded by the graph of f, the x-axis, and the line x is equal to 1. So essentially what we are going to do is find the area from 0 to 1 of f of x dx. Now, you probably will notice that we're still using the same function, and we don't have any asymptotes here between 0 and 1. That being said, what I'm going to do is just copy what I have right here, because we're not doing anything new, but change my bounds so that we don't have this. Change my bounds so that it is from 0 and 1. So now I have 1/5 ln of, let's see, 1 minus 3 is negative 2. 1 plus 2 is 3 minus ln of negative 3 over 2. And this is okay as an FRQ. This is your final answer. Now I'm going to take it a step further. Let's say that this was a multiple choice question and your answer was simplified. Well, if it's simplified, you're going to have 1/5 ln of 2/3 over 3/2. I took the absolute value of negative 2/3 and the absolute value of negative 3/2. That gave me 2/3 and 3/2. Because this is a minus sign right here, I'm going to use the quotient property. So I have this 2/3 divided by 3/2. This is the same thing as 2/3 times 2/3, which is 4/9. So I have 1/5 ln of 4/9. And I'm going to take it a step further again for the LOLs. That's the same thing as ln of the 5th root of 4/9. Of course, that was just extra information, for the LOLs. Don't do this if you're not comfortable with the algebra. If you want to keep it like this on the FRQ, that's fine. The reason why I showed you this is because this might pop up on the MCQ where you get an answer, but it doesn't look like one of the answers that you see on the MCQ. All right. So this is the last video for Unit 1. That being said, study for Unit 1, and we're going to have fun with Unit 2.